Okay, welcome everybody, and thanks for joining this webinar. I am Andrea Bidoli from CSE Italia, and I'll be the speaker of this event. Today, I'll show you an introduction to the program VIS, which works as a detailed post-processor of the CSI America's software SAP2000 ETABS CSI bridge for the design of reinforced concrete structure. In particular, we will see how the program can be effectively used in the design of a 5 stories ductility class medium seismic resistant structure compliant with the provision from both Eurocode 2 and Eurocode 8. For this example, both static and dynamic analysis of the building have been run using SAP2000 software, while this will be used for the detailed design of the reinforcing on the structural members. We will briefly go through all different stages of the design, and we will see how to perform detailed checks in terms of strength, capacity design, serviceability design, and detailing provision as well. This first live webinar is intended to serve as a general introduction to the program, and we are going to deepen particular aspects of the design during future dedicated events, basing primarily on the feedback that we will receive from you at the end of the webinar. Okay, before going into the details of the example, I would like to spend a few minutes, I promise they will be only a few minutes, to introduce the company I work for and to explain why the VIS program has been developed and how it grew through the years. Okay, CSE Italia is the official channel partner of CSI America since 1990. As we all know, CSI America is the developer and the distributor of the most advanced programs for the finite element analysis of buildings, civil structures, and infrastructures like SAP2000, ETABS, CSI bridge that have been used worldwide to design the most iconic building of the modern era. We are so the official channel partner of CSI America for the Italian territory, and we provide sales service, dedicated technical support, and advanced training to all the Italian users. Since 2006, also, CSE Italia started the development of VIS, which is basically a software package for the design of reinforced concrete structure based on the Italian and the European codes, which works as an independent post-processor for the CSI programs SAP2000, ETABS, and CSI bridge as well. This is not a unique program, but it basically provides a family of plug-in tools that are fully integrated with the CSI programs and are capable of enhancing their design features to a higher level of detail. Basically, the VIS suite is composed by 4 different programs. One is the main program itself, which has an independent user interface and which is used to obtain detailed checks for each limit state, and as several exporting options, we will look at the main program in detail during the webinar. The second tool is Section Cutter, which is an automatic tool for the definition of section cuts through wall stacks or coupling beams in SAP2000 CSI bridge. It is not necessary in ETABS, since ETABS already has the pier and spandrel labeling option embedded in it. Then there is Combinator, which is a tool for the automatic definition of load combinations according to Eurocode 0 and 1. And the last one is SPF, which stands for Seismic Performance Finder, which is an optional module for the automatic seismic rating of existing reinforced concrete structure. SPF basically works running a set of incremental dynamic analysis varying the seismic intensity with the purpose of finding the critical level of the seismic force that the structure is able to withstand. Currently, it is based on the Italian code only, but of course we plan to make it compatible with the Eurocode as well. We all know that the CSI programs already include powerful reinforced concrete design tools according to the main international design code. So at this point, the most common questions that usually arise from our potential users are: how can VIS enhance these capabilities, and why these features are not integrated within the main analysis software? Well, to answer both these questions, I first need to briefly explain why we initially decided to start the development of the program. I've just told you that the development of this started back in 2006, almost 15 years ago. And the reason was that across approximately 2003 and 2005, two, I can say, revolutionary design codes were published and became the reference for the design of new buildings here in Italy, but in Europe as well. These codes were the Italian OPCM 3274 and the new version of the Eurocodes, particularly Eurocode 2 edition 2004 and Eurocode 8 edition 2005. Well, this new document introduced breaking changes to the whole standard design approach and a lot of new requirements to be fulfilled. From that time, basically all the supervisory committees and all the other related authorities started asking for detailed checks and reports compliant with the new prescriptions. And for basically this reason, we realized that we need to provide our user with integrative tools to cover these new requirements. And since the Italian code and the European code were very similar, we decided to cover both of them with this. Okay, so after this small introduction, I'm ready to answer to the first question, which is how this can enhance the capabilities of the CSI program. Basically, because as I said, it allows for a direct calculation of demand capacity ratio for all the different limit states, which means strength, capacity design, serviceability design, and also detail and provision. And it allows for a full customization of the reinforcing. We will see it later. And the second option is that basically we all know that design practices are very different from country to country, and this has been fully designed, I say, to follow the European Common Construction Practices. So it has been basically developed basing on the common practices that we have here in Europe. The second question is why the VIS suite is not directly integrated in the main software. Well, this question is less obvious than the previous one, but basically we all know that the core of the design of a structure is the analysis process. So when we have to run the analysis on a structure, we need a tool which is very effective in doing that, but at the same time easy to use. And we all know that the beauty of the CSI America's software is that despite they are the most advanced programs in the market, they are also the easiest to use. And CSI America is always putting a lot of efforts to maintain the productivity of their software to the highest degree. Instead, we know that the detailing phase is quite distinct from the analysis phase, and it also requires different interfaces and tools. And so basically, embedding all these features in a unique software would probably result in a poor user experience and a lower productivity. The second answer that we have for this question is more practice, and it is the fact that VIS has basically its own licensing system, so the detailing process can be done independently once the model has been imported from the analysis software, and so the license of the main software, whether it is SAP2000, ETABS, or CSI Bridge, can be used from others while we are performing the detailing part in the VIS program. Okay, let's now see very briefly which are the main features that the program offers. Of course, we will see this feature in more detail later in the webinar. The first is for sure the design wizard, which is a tool for the automatic definition of reinforcing on beams, columns, walls, and coupling beams based on user-defined preferences, which means that the user, once he has completed the import of the structure in VIS, can select some rules and some preferences that he wants to use in his design, and then VIS will populate all the elements with the required reinforcing in terms of strength, capacity, and detail and provision. Users will then have simply to check if the reinforcing provided by the program satisfies all these requirements, maybe make some minor adjustment, and he is done with the design. The second important feature is basically, as I mentioned before, that the reinforcing is fully customizable inside the program. There are dedicated tools to customize reinforcing on beam rows, column rows, and shear wall as well. We will see these tools in detail later. The third feature is that the program provides explicit calculation of demand capacity ratio, and we cover basically all the different limit states, which means that we provide the calculation of strength demand capacity ratio, both for PMM and shear. We cover capacity design, so we provide demand capacity ratio in terms of shear in the primary beams, shear in the primary column, check of weak beam, strong column condition, which is basically the design of the flexural behavior of joints. We cover also the design of the joints in the primary joints in shear, and we cover all the prescriptions related to the capacity design of walls, whether they are ductile walls or large lightly reinforced walls, both in terms of PMM and shear. And the same for what concerns the service limit state. We provide direct calculation of cracking, working stresses, and soon deflection checks in the members. Another important aspect of the program is that it checks also basically the detailing provision that the codes provide. It basically perform the check of the minimum required areas and a lot of other different provisions that need to be satisfied from a detailing point of view. And another important feature is the possibility to export the reinforcing that have been assigned through the program in several different formats. The most simple one is tabular Excel spreadsheets. Then the reinforcing layouts can be exported in CAD format. And again, soon we will see this in the webinar. It is still not available in the current version of VIS, but soon it will be possible to export the full 3D model, reinforcing included, in the IFC format. The last feature that we want to mention is the automatic creation of the calculation report, which will include detailed all the details of the different checks and conventions that have been used in the design process. Okay, we just saw that the program already does a lot of stuff, but since we strive to always improve our products, we are mainly interested in knowing from you what the program is instead lacking and what we need to enhance or implement to make the program more productive. For this reason, at the end of this webinar, you will be asked to answer to a small survey that would hopefully allow us to collect some useful feedbacks. The last thing I would like to talk about, then we will switch to the example, is the pricing policy. Here you can see the VIS pricing. We divided the world into two different pricing areas. The prices you see here are referred to region 1. Countries that are falling in region 2 are currently receiving a flat discount of 60%, recognizing the disruption that COVID-19 is bringing to the world economy. So if you're interested in having a quotation or in any other technical or commercial aspect, feel free to contact us and visit our international website, which is plenty of useful content, both related to the program, but also some interesting detailed videos on the different part of the program. We are keeping improving this watch and learn section of the website. So this is basically the reference for obtaining any information on our software, and here you can also directly contact us for any aspect related to the program. Okay, I think we are now ready to start looking at the example. So let me close the presentation. Okay, the example we prepared for this section is basically a 5-story reinforced concrete structure to be designed according to the provision of both Eurocode 2 and Eurocode 8. As I mentioned, we use SAP2000 as structural analysis software. The structural behavior of this building has been assumed as dissipative, and the chosen ductility class is medium. Each floor is made up of one-way ribbed slab oriented along the global X direction, and we can take a look at it. Okay, this is a plane view. Let's change also the colors of the objects. Okay, so basically these represent the one-way slabs that have been modeled by means of non-areas with the purpose of assign the loads to the beam, because this one-way ribbed slab are supported at each span by hidden beams. In Italy, we used to call them in-depth beam, while I see that in English it's more common to call them concealed beams or hidden beams, which are beams that has the same depth of the slab. As we can see, the orientation of each of these load area is the X direction, as we mentioned, while the lateral force resisting system is different in the two principal direction. We have a set of primary moment resisting frames in the X direction. We can also see the layout of those primary moment resisting frame. Okay, so we have this internal moment resisting frame and some moment resisting frames on the edge of the building, while in the Y direction a set of ductile walls has been employed. Okay. The basic reference seismic intensity is defined by a peak ground acceleration of 0.25 G. We can see the reference design response spectrum here. And even if the moment resisting frame could have allowed for a larger ductility, a unique overall behavior factor of 3 has been assumed in the design for both the horizontal directions. The last thing I wanted to specify is that for this project, all the concealed beam, the hidden beams, have been assumed as secondary seismic elements, and therefore their contribution in terms of strength and stiffness must be neglected in the design. In order to be allowed for this assumption, we checked that all the requirements provided by Eurocode 8 were satisfied, and one of the most important of this requirement is to prove that the contribution in terms of stiffness of the secondary elements is lower than the 15% of the overall stiffness of the structure, and that they do not significantly affect the dynamic behavior of the building. At this purpose, we compare the dynamic behavior of the building using two different stiffness scenarios. The first one, where all the elements have been considered as active. So this is the full stiffness scenario where we added all the elements. And this is the second stiffness scenario where we added all the elements but assigned a release to the secondary elements in order to exclude them from the lateral load resisting system. And then we run basically two different modal analysis, one considering the full stiffness and the other considering only the stiffness from the primary elements. In both cases, the effect of cracking in the primary elements has been accounted by the application of appropriate stiffness modifiers. In this case, by simply looking at the results in terms of dynamic behavior, we can prove that our assumption on the secondary element is correct. So we can quickly take a look at the result. We can now look at the modal behavior of the structure with the full stiffness. Okay. So we can see that the behavior of the structure is fairly regular. This is the first mode. This is the second mode. These are two basically pure translational mode. And this is the behavior of the structure considering the full stiffness. We can compare this with what we have obtained considering only the stiffness of the primary element. Well, the first mode, of course, didn't change because secondary elements only affect the behavior in the y direction, while second mode slightly increased in period, but this is expected, and the increase in period is lower than the code maximum prescribed difference. So we are basically allowed to consider all the hidden beams as secondary elements. We will now go further into details of this aspect now, but if you're interested in this topic, we can for sure make a detailed focus in one of the next webinar. I am only going to spend a few words to clarify how we handle the design of the secondary elements in VIS, since the code gives us essentially two different options. The first option is to design the secondary elements so that they remain elastic when subjected to the displacement caused by the most unfavorable seismic design condition. And the second approach that we are allowed to use is to design the secondary elements so that they basically yield when subjected to the displacement caused by the seismic condition, but in this case, they need to possess adequate ductility to maintain the support of gravity loads. In this case, we choose the first option, so we choose to maintain the secondary element elastic, even if it is not probably the best choice from an engineering point of view. And we will see how to satisfy the corresponding strength requirement using VIS. Basically, what we did is to create two different response spectrum function, one with the behavior factor that we choose for the primary element, which is 3, as I mentioned, and another one with a unit behavior factor. This second response spectrum will be used for the analysis of the stresses in the secondary elements, so that in this we will be able to import different seismic load combination for primary and secondary elements, and we will see this in a minute. Before start looking at how the structure can be imported and the design in this, I would like to introduce two of the other two that compose the VIS suite that are section cutter and combinator. First of all, let's see how combinator can be used to generate load combinations according to Eurocode 2. So the first step when we launch combinator, that can be, as you just saw, executed from the tools menu of SAP2000, is to select which load cases should be used for generating the load combination. And in this case, we don't want to use these two load case, but only the one that I just selected. And we have to pair each load case with the corresponding load type. So in this case, this represents the residential live load. So I will pair it with the corresponding load type by the code. As you can see, load types are identified using the same convention of the design code, so it's quite easy to pair each load with the corresponding load type. Once we have done that, in the right part of the window, a set of filters can be activated normally to exclude meaningless load combinations. So we can activate the filters that basically avoid the program for creating those that normally are load combinations that do not affect the design. And finally, we only need to select for which limit states the load combinations should be generated. Again, the name convention is identical to the one reported in the code, so it should be quite straightforward to identify the different types of load combination. Here we have the strength load combination used for the ultimate limit state design. Then we have the quake load combination. Then we have the service load combination that are divided into characteristic, frequent, and quasi-permanent load combinations. Once we're done, we can generate the load combinations, and we can review the load combination directly inside the SAP2000, because load combination have explicitly been added to the SAP model, so we can take a look to all the load combinations that the program defined. And if we want, we can edit them using directly the SAP interface or the interactive database editing. Okay, so this was part related to Combinator. And then the second plugin I want to show you is Section Cutter. We all know that usually shear walls are defined in SAP, ETABS, or CSI Bridge using assemblies of concrete shell elements, and in this case we have done exactly that. And so for the walls to be imported in the VIS model, they need to be preliminarily cut into a series of sections that should be taken at a finite number of locations along the length of the wall and organized into wall stacks. In ETABS models, as I mentioned before, this can be easily done by using appropriate piers and spanner labels that are automatically identified and imported by VIS. Whereas for models created in SAP2000 or CSI Bridge, this preliminary step must be done using Section Cutter. And we will see in a minute how easy it is to define wall stacks in SAP2000 using Section Cutter. The first step is to select the elements that made up the wall stacks and launch Section Cutter. Once the plugin starts, we have several different options. There are two simplified commands to define vertical wall or coupling beams, and then there is a general command to define general sections using group. In this case, we want to define a simple vertical wall. So the first thing to do is to select the wall name, and then to select at which locations sections design section must be generated. Normally, sections are created at each grid level, so at the top and the bottom of each grid level, but the user has also the option to increase the number of this location by selecting joints along the wall stack and activating this option. And there is also an option to create separate legs for shear design of complex wall shapes, like, for example, concrete cores that has more than one leg. So the program will create a unique section cut for the purpose of performing the flexural design, but it will keep separate section cut for the shear design of the wall. In this case, the wall is simple, so we simply need to click OK, and the program just created the section cut. Again, section cut can be seen directly in the SAP definition menu, but in this case we do not need to change anything because this information will automatically be interpreted by VIS, and the wall stack will be automatically recognized. So let me open the full version of the model where I have defined all the different walls and load combinations, and we are now ready to basically run the analysis and import the model in VIS. Before showing how the model can be imported, I want simply to spend 2 words to describe again the policy for designing secondary elements. We see that I have created these 2 seismic load combinations using Section Cutter, which basically includes the response spectrum analysis for primary elements. I have also created a copy of these 2 load combinations, which instead include the response spectrum analysis that I need to use for the design of the secondary seismic element. Okay. Once I start VIS and I obtain the import definition window, I can choose which load combination I want to import in VIS for the design of the structure. Combinations are organized by limit state. So the first are the ultimate limit state, which includes all the static loads. Then we have the ultimate seismic load combinations. Okay. Then we have the characteristic load combinations for serviceability design. Then the frequent load combinations, and last, the quasi-permanent load combinations. If in my structure, I don't have any secondary element, I'm done and I can click the OK button. But in this case, we also have secondary elements. So I need to go to this tab and tell the program which are the secondary elements. In this case, I have created a group which includes all the secondary beams, and also tell the program which are the load combinations to be used for the seismic design of secondary elements. And in this case, I select the two load combinations that I just showed you that are basically being defined with the purpose of designing secondary elements. So now I'm ready to start the import. And so the program will automatically import both primary and secondary elements and assign them the proper load combinations for static and seismic design. Okay, we just finished the import. And what we have obtained so far is basically a copy of the entire SAP model in terms of geometry, materials, and internal forces. If I select, for example, a cone, I can see that the material has a cylindrical strength of 28 megapascal, which was the value that I had assigned in the SAP model, and the reinforcing is the one that I assigned by default in the SAP model. This reinforcing is meaningless from my point of view because we are going to design the reinforcing completely in VIS. If I select a beam, for example, in SAP I didn't define any reinforcing, and indeed I have a dummy reinforcing here in VIS. So we imported the geometry, and we imported also, as I mentioned, the internal forces in the elements. Okay, so we have all the different load combination and the different limit state, and the same apply for shear walls. Okay, so we can show this is the bending moment diagram of the shear wall, and we can look at the different diagram forces. So we are now ready to start the design of this structure. The first step we need to do to design the structure is to correctly set the code settings. In this case, the code is correctly set as Eurocode 2. We want to use the seismic provision included in Eurocode 8, so we check the seismic options here. And then we have to set the general and detailed parameters that we want to use for the design. So we can choose which are the basic partial factor for the materials. We can set different options for the calculation of the bending strength, the shear strength. We can choose how to handle imperfection and also second order effects. We can tell the program if we simply done a first order analysis or if we have done a second order analysis with both a small and large P delta effect. We can choose which method to be used to calculate the second order effect in the elements, if the structure must be considered as a sway or non-sway for the purpose of calculating effective lengths. In this case, the structure is basically dominated by lateral forces, so we will not have a structure which is subjected to high second order effect because the size of the elements are quite squat, so we don't have slender elements in this case. Then we have to set the correct seismic behavior. In this case, we want to use ductility class medium, the curvature ductility factors that should be set according to the behavior factor that we used in the definitions of the response spectrum. In this case, the basic behavior factor was 3, and the curvature ductility can be approximated as 2 times Q minus 1, which is 6 minus 1, which is 5, and that's why we see that here the curvature ductility factors has been set to 5. And then we have to basically specify some parameters related to the shear wall capacity design. In this case, the program is asking the spectral acceleration corresponding to the TC period and the T1 period. In this case, they are identical, and also the reference behavior factor, and also if the structure needs to be considered as dual system or not. In this case, in the Y direction where the ductile walls are active, the behavior is not a dual system behavior, but is a simple shear wall behavior. So we will leave this as it is. And the last thing we have to set are the serviceability settings. In this case, we want to check the crack opening, and the limiting crack opening that we consider to be okay is 0.5 millimeters. And here we can also customize the stress limitation factors for the different design load combinations. Once we are done with that, we are ready to start the design of the structures, of the structure. Before start looking at the true design process, however, I would like to make a brief descriptions on how the reinforcing is handled inside the VIS software. Okay, we just saw that once I have imported the structure, even if this beam was modeled as unique elements, I've showed you that it has been internally organized into different sectors or segments, as we call them in VIS. So let me now open a reduced version of this model for the purpose of showing you how reinforcing can be easily handled inside VIS. So I'm going to open a small portion of the same structure, okay, like it was imported from SAP2000. Again, if I select this beam, I will see the dummy reinforcing that has been initially assigned by VIS. We all know that in general, the reinforcement along a beam or a column itself is variable, and also the corresponding strength varies accordingly. Thus, in order to allow for general reinforcing configuration, in VIS, every frame element can be internally organized into an arbitrary number of segments. Okay? As I mentioned, a segment is basically a portion of a beam or a column which extends for a certain length. Okay, in this case, and the length of the beam is 5.75 meter, and the length of this segment is 1.92 meter. So a segment is a portion of a beam which extends for a certain length and the corresponding sections associated. In this case, all the 3 segments of this beam has the same section, which is called TR 60 by 25. A section is basically a combination of a certain concrete shape and its longitudinal and transverse rebar. So a section includes both the shape of the section itself and all the reinforcing assigned to it. So using this segment section pattern, it is basically possible to replicate any layout in a very simple way, and we will soon see how. There are essentially two different approaches that can be used to define the reinforcing along the elements. The first approach is basically what we call define, split, and assign approach, which is probably the more straightforward, while the second is represented by the use of dedicated reinforcing editors that are available for beams, columns, and walls. We're going to see a brief example of both of them. So let's suppose that we want to divide all the columns of this frame that we have here in three different segments that has the same longitudinal reinforcement, but a different transverse reinforcement with a closer spacing into the external segments. And let's assume that we want that this segment to be to have a length equal to the critical length of the different columns. So the first thing to do is to define the two sections that we want to use for the different segments. So we start for the basic section, we create a copy of this section, we change the name, so this will be the section used in the critical segment. We customize the reinforcing of this segment. For example, we put 5x7 reinforcing. We use D20 for this example. Then we also customize the transverse reinforcing. So 4 legs in 3 directions, 2 legs in 2 directions. Okay, the D8 is fine, spacing 10 centimeter. Okay. And then let's create the section that we want to use for the central segment, which we will call non-critical. And in this case, we will simply reduce the stirrups since this region and increase a little bit the spacing. Okay. Now, what we have to do is basically to select all the columns, split the columns into the number of segments that we want. In this case, there are automatic options to split segments in 3 parts, to split elements into 3 parts, where the end segment's length is equal to the critical length. I click OK. So now all the columns have been divided into 3 segments, and the length of the external segments is equal exactly to the critical length. Then I can reselect all the column and assign them to each segment the correct section. So in the external segment, I am assigning the critical section. In the internal segment, I will assign the non-critical section. Okay, in this case, I can select any of the columns and see that the reinforcing has been correctly assigned. We can see it from here, or by looking at the reinforcing sketch that is available here. So in a very simple way, I basically divided and associated the reinforcing on all the elements. This is one way to do the job. The second way, as I mentioned earlier, use a dedicated tool that is very powerful and allows for the definition of the entire reinforcing along a full beam row or column row. For example, if I select the beam 266 and I go inside the reinforcing editor, I can see the whole reinforcing not only in this beam, but also in the other beams that is in the same beam row. So by moving the cursor here, I can move along the different sections, the different stations of these beams. In this case, the reinforcing is uniform along all the elements, and so I don't see any difference, but we will soon see how the reinforcing can be easily customized. So let's start to customize the reinforcing. I select all the rebar, then from here I can delete all the position. I can go inside the section and start defining the basic reinforcement, which will be defined by 4 D16 rebar. I can also specify the basic shear reinforcing, which is made up by D8 rebar with 4 legs in the vertical direction and the step of 15 centimeter. Okay. Now I can again select all the position. I can extend the segment until the end. Let me move the panel of the webinar. Okay. I can extend this to the end of the beam, and I can do that for the transverse reinforcing as well. Okay. So now I have assigned a uniform reinforcing over all the elements, but probably this is not what I want to do, because maybe I need to add some additive negative rebar at each support. So let me put here the cursor and go back into the section and add some additive rebars in the upper part of the section. For example, 3 additive rebars equally spaced. Okay, and then I can specify the length of each segment of additive rebar. I will do a symmetric layout in this case. Okay, and I want to do the same in the middle segment of the section. In this case, I put only 1 additive rebar in the middle. Okay, here I will snap to the center of the beam, and I will have an extension of 1 meter and 1 meter, and the same from in this. Okay, in this side. Okay, with few clicks I've created a very complex reinforcing pattern in my beam, and I can also check if this reinforcing pattern is fine. As you can see from the color scale that you see in the bottom part of the window, there are some regions where this reinforcing is not okay. For example, here, okay, I also can see why the reinforcing is not okay. In this case, the moment capacity is not enough, while for positive moments, I do not have any problem. Okay, I'm already at a good optimization level. Okay, what I can do is simply select the additive stills, and I can probably pass to 5 stills instead of 3. Okay, the reinforcing have been updated in all the beam row, and I can rerun the check and see that now I am perfectly compliant with the strength requirement. Okay, I can also look this in 3D view. In this case, it's not interesting since there is no axial and minor bending. So if I'm satisfied with this reinforcing layout, I can also decide to copy this reinforcing layout to other similar beams. Let's suppose that we want to copy this reinforcing layout to all the secondary beams that I have in this model, which are the ones that are highlighted here. So I simply basically have to create a groups that I already created here, going back into the reinforcing editor and click on copy reinforcement on secondary beams, click OK. Okay. And now I can see that all the beams have the same reinforcing assigned. So it's very straightforward to basically customize reinforcing in beams and columns. The same can be done also for shear walls. We will see an example also for the shear wall. I select this shear wall. I go to the reinforcing editor of this shear wall, okay, which is very similar to the one of the beam. Here I can see the sections that I have defined. I can move through the different section with the table in the left, or I can directly click in the 3D view, okay? So let's go to the base section and define a quick parametric reinforcing. For example, we choose a cover of 5, we choose the rebars in the end region, okay, with 10 centimeter step. In the central region, we can use D12 with a spacing of 10. And as shear reinforcing, we can use D10 with a spacing of 10, and cross ties, we can use 3, 6 is fine, and probably 10 centimeter is correct. Okay, and I have assign this basic reinforcing to the base section. I can copy this reinforcing. I can extend this reinforcing to all the critical section. As you can see, by moving the cursor, I have the same reinforcing in all this section. Here, I still have empty reinforcement, so I can go back here and put a uniform reinforcing here, for example. Okay, let's use it. 20. No, internal region. Okay, step 10. Here I can increase the spacing, and also here I can. Here the number of cross ties is not so important. I can also put 0 cross ties, and then I can copy the reinforcing in the remaining sections. Okay, and I can now I have all the reinforcing defined throughout all the shear wall in very few steps, and I can check the wall in terms of strength, shear, PMM, capacity, shear capacity. So maybe in this case, it's more interested to look at the PMM capacity. So the program automatically performs the translation of the bending diagram and check that all the sections are compliant. So we have just seen how easy it is to manually define the reinforcing in all the structural elements, but fortunately, usually for the design of new structure, this preliminary step is not required, and we will see why is not required. As I mentioned, okay, let's see if there are any questions for the moment. Okay, I don't see any questions, so I can continue with the webinar. Okay, as I mentioned before, VIS implements an automatic tool that we have called Design Wizard, which basically has the function of assigning the necessary amount of reinforcing to the different members basing on user-defined preferences. So if the elements are correctly proportioned, the reinforcing provided by the wizard will be compliant with strength requirements, capacity design requirements, and most of the detailing provision requirements. So at the end of the process, the user would only need to make minor adjustment to the result reinforcing configuration. So all the steps that we saw before are normally not necessary, or the user just needs to do some adjustment on few elements and maybe replicating those adjustments in other elements. The steps that I showed you before are mostly useful in the case of existing structure where the reinforcing is already defined and you need to check if the structure is still compliant with the new provision. Okay, I see that there is a question. Okay, question by Nick. What are the shaded areas in the walls? Okay, Nick, I'll answer to this question now. The shaded area in the walls are the so-called confined region. Let's see it again. If I go into this wall, the base section, the first and second section, so all the first level of the structure is considered critical, so confined regions need to be provided, and in the confined region you must respect some provision related to the flexural and transverse reinforcing. So this basically highlights those areas because he recognizes that they are critical areas. Okay, I don't see any other questions, so we can start looking at the design wizard now. So the design wizard has a dedicated panel inside the program where the users can basically customize the settings that they want to use for their project. So strictly speaking, users can basically select which diameters to be used for the design of each element, and also the covers that the program needs to consider in the design of the elements. Then there are also some additional options to force a symmetrical reinforcement layout, to increase the bottom reinforcing to account for creep, and other detailed options. The same applies for the column, for the transverse rebar of beams and columns, and for the piers reinforcing and the spandrel reinforcing as well. As you saw, you can specify one diameter if you want to use exactly that diameter, or a list of diameter. In this second case, the program will choose the best diameter, both considering cost and constructability. Okay, so in this case, we wanted to use certain specific diameter for primary beams and secondary beams, and also for the columns, while for what concern the shear walls, we'll let the program decide which reinforcing is the more appropriate for each element. Okay, once we have set all these parameters, we are ready to start the wizard. We can run the wizard on all the frame elements, on all the wall elements, on all the elements at once. And if we select a particularly set of elements, we will run the wizard in the selection only. So the wizard can be also run several times using few elements at a time, and this will allow you for changing the reinforcing preferences or other parameters that you want to differentiate between different set of elements. In this case, I don't need to do any distinction between the different categories, so I will run the wizard in all the structural elements at once. As I mentioned, at the end of the wizard, we will hopefully obtain a detailed reinforcing layout that would be compliant with all the strength, the capacity, and the detailing provision requirements. And we will see as the wizard will be completed what I mean with that. Okay, the wizard finished the job. We don't see any warning message here, so hopefully all has been completed without any errors. Let's see what we have achieved. So the first thing we can do is to take a quick look at the assigned reinforcing. We can do this either looking at the reinforcing maps that are available here. So for example, I want to look at the reinforcing ratio contours on columns. I see that all columns are inside the limit, the upper limit of 4%, but I have some congestion of reinforcing in this column row here, while all the other columns row are quite okay from this point of view. I don't have a lot of reinforcing concentration in other in element different from this column row. We can do this for the top reinforcing of the beams, and I see that here I have almost 2% of reinforcing in this secondary beam, and this is due to the fact that this secondary beam must remain elastic with the displacement at the ultimate limit state, as we saw before. So probably the best choice for this secondary beam was not to design it to remain elastic, but to be ductile. Normally, this allows us to save some reinforcing, and the same for the bottom reinforcing of the beam. So we can look at the reinforcing using this useful colored map, but we can also, as we saw before, select, for example, a beam row and take a look at the reinforcing using the reinforcing editor. So these are all the different span of this column row. Let me turn on the label. Okay. So let's go back to the reinforcing editor. So this is the first span, second span, third span, and this is the reinforcing that the program has designed for this row. Okay, this was a seismic beam only, no gravity loads on this internal beam, because as we saw before, the slab run parallel, the ribbed slab run parallel to this beam. So these are basically seismic beams only. So we can take a look at the reinforcing using the color maps, using the reinforcing editors, but also selecting any elements and take a look at the reinforcing sketches that the program can give us. Okay, from the first look, we see that the reinforcing are inside the code maximum allowed, but we saw that there are probably some elements that maybe should be enlarged to have a lower reinforcing congestion, or maybe designed using a different policy. We will see this in a minute. We will come back to this later. Let's now check if the reinforcing assigned that we briefly saw now is conforming to the necessary code request. And we can do this step by running all the different checks. So I move to the strength menu over there, and I ask the program to perform the checks of all the frame elements, then all the wall elements, and the same for the capacity design of both beams and walls, the serviceability design of beams and walls, and last, the detailing provision. Results, as we can see right now, can be easily reviewed by means of overall controlled views, or alternatively summary table. For example, I can move to the result tab and see. Let me show the PMM demand capacity ratio. I can see them also on a segment by segment basis. In this case, I can see how the reinforcing is differentiated in the different segments, and the same can be done for the shear strength check, for the capacity PMM checks, and this is done only for primary columns, and of course shear wall. We can see that the design of column, as expected, is dominated by the capacity design, because column must have a strength which is higher than those of the beams framing into the primary columns. This is the so-called weak beam, strong column condition. We can take a look at the shear capacity design. Also, this is a critical check for most of the elements, and this is expected since the seismicity of the level of seismicity considered in the structure is quite high. And then we can take a look at the service stresses, and as expected, service stresses are basically critical in the hidden beams or concealed beams, while there are not a problem in the primary seismic beams, and the same for cracking. So basically all the checks are satisfied. As I mentioned, we can look at the checks from the graphical interface. This is probably the most user-friendly approach, but we also have detailed tables which report the checks for any beams and columns organized by segment. So, for example, the program tells us that beam 241 has 3 segments, and he basically finds which are the critical combination for each segment and reports the internal forces, the reinforcing areas, and the resulting demand capacity ratio. The same applies for column, for shear, and for example, for capacity design. both in shear and PMM, and so this gives us basically full control over the checks of each element in the model. Apart from that, for each element and each limit states, design details are available also through dedicated commands. For example, if I want to take a look at the PMM strength check of a certain column, I can select the column and look at the PMM check of that column, and I can see the most critical demand capacity ratio. Okay, here we can see this red dot, which identifies the upper compression limit that must be fulfilled from primary column, and I can take also a look in the 3D view of the interaction surface. I can do the same, for example, for the serviceability design of column. Let's take this column over there. I go to the serviceability stress limitation, so we can see the neutral axis, we can see the resulting compression and tension in the element. So for example, I can look at the deflection check of this beam. Okay, so basically we have the control, the full control of every check that the program does internally. For example, quite interesting is to see the demand capacity ratio related to the weak beam strong column condition, okay, of, for example, this joint here. We can see that the red domain corresponds to the possible flexural hinging of all the 4 beams framing into this joint, and the green area is basically the available strength from both the top and the bottom column. So this check is made both for the maximum and minimum axial check, and the same as we've seen before can be applied for shear wall. For example, we want to look at the PMM check of this wall. We can look at the enveloped bending moment diagram or to the amplified shear diagram. Okay, so all these checks are performed automatically by the program and can be reviewed in the detail from the user. So basically, users have access to all the details of the calculation in order to check if they are conforming to the code prescription. Okay, let me know if there are any questions about this aspect. I would like to spend a few words on commenting the result we have obtained in terms of reinforcing. So I will plot again the reinforcing ratios of all the columns that we have obtained here. As we saw, we have quite a high level of reinforcing on this column. I can select the column to see it better using the reinforcing editor here. Okay, so we have a lot of flexural reinforcing required to this column from the base basically to almost the top of the column. This configuration, okay, is a direct consequence of one of the options that we used when we executed the design wizard, and in particular the fact that we do not have checked the free column reinforcement option. So basically the demand of reinforcing in the columns can generally be lower in the lower stories than in the upper stories. In this case, this is especially true because since the capacity design of the joint govern the design of the column, basically the beams that framings into the joint at the different level has the same amount of the reinforcing, but the axial force in the column is higher in the lower story. So in the lower story, the demand in terms of capacity design is lower than in the upper story. For example, if I select this joint and I go to the capacity check, I can see that the demand capacity ratio is far lower than the one obtained in the upper stories, which was nearly equal to 1. Okay, so in general, the reinforcing can be decreased from one story to another, but by default, we do not allow this. So if you want to use the free column reinforcement, you can activate this, and the program will design the columns allowing from reinforcing in the bottom story to be lower than reinforcing in an upper story. If this option is not checked, the reinforcing in lower stories will be at least equal to the reinforcing in the upper story, okay? And that is exactly what happened here. So this was the most critical column, and all the columns below this were assigned exactly the same amount of reinforcing, okay? If we want, we can change this, but if we change this, we probably have problems in the splicing regions, because if we leave the splicing at the base of the column, like we did in this case, we basically face the problem that at a certain level we need to anchor a higher level of longitudinal reinforcing into a lower reinforcing coming from the bottom story, and this can create constructive problems. So that's why we normally do not allow this unless also this option is checked. So I advise that if you want to use the free column reinforcement, the splices should be done at the middle height of the elements. In this case, we will also have the problem that we have to anchor a higher amount of reinforcing into a lower amount of reinforcing. But this will be done in the middle of the column, where normally the bending stress is barely 0, and so this will not be a problem from a constructive point of view. So let's see what happens if we change this design policy. So I select only the columns, since I don't want to redesign all the structure. I check these two options in the design wizard, and I run the design wizard in the column only. Okay, if now I look at the reinforcing ratio in the column, I can see that I have a high level of reinforcing only in the column across basically the 4th floor of the structure, while in the other levels the reinforcing ratio is lower. Okay, so if we want to take a look at what happens here, I can select this column and see the reinforcing sketch here. I can see that the reinforcing in the middle, okay, varies from 22D20 to 10D20. These are the corresponding sections. And also in the lower story, the reinforcing varies from 20D20 to 22D20. So the reinforcing increases in the upper story, but since the splicing are made in the central region, this won't be in general a problem for a construction point of view. And in this case, as we see, we obtained in general a lower density of reinforcing overall the structure. Okay, so we've seen how to take a look and eventually customize the reinforcing on beams and columns. The last aspect I want to show you before looking at the export capabilities is to look at the reinforcing in the shear wall, because we saw that all the checks were satisfied in the shear walls, but we didn't look at the reinforcing that have been assigned to the different shear walls. So for example, select this first wall and see, okay, the reinforcing that have been used. Okay, here I have some code prescriptions that are not satisfied because the program does not automatically place the transverse reinforcing into the critical region, but we will see later how this can be easily accomplished. We decided not to automatize this aspect because it's basically more related to a detailing aspect that the user need to figure out how he want to perform this kind of to accomplish this kind of detailing. But in this case, what I don't like is that the reinforcing in the confined region is very high, and again I can have a problem when I have to splice this reinforcing probably in the upper story. So I would like to reduce the amount of reinforcing in this region, and what I'm going to do to achieve this is going into the general settings and tell the program that the maximum allowed reinforcing ratio in the confined region is not 4%, but rather the 3%. Okay, then I simply select all the walls and again run the design wizard on the walls only. In this case, the program redesigned all the walls, and I can take a look at what changed. In this case, I see that the reinforcing in the critical region reduced. Before I had 9 rebars, longitudinal rebars. Now I have only 7 rebars, and of course, on the contrary, the reinforcing increased in the middle region. But to me, this is a better configuration than the other, so I would go with this configuration. We can also rerun the checks to be sure that this new this change doesn't broke anything. Okay, so I can take a look at the strength. All the shear walls are okay. Strength in terms of shear, PMM capacity, and shear capacity. So in this case, we basically managed to customize the reinforcing, or better, to force the design wizard to use less reinforcing in the confined region in order to achieve a better configuration from a constructability point of view. Okay, let me know if there are any questions, or I think we are ready to move to the exportation option, which is the last thing I like to show you in this webinar. Let me open the full model. Well, I also added the below grade walls, and I have customized the reinforcing, the transverse reinforcing in the confined region of the walls. I open the same wall. Okay, and you can see how I satisfied the confinement requirements in the critical region. Basically, I put 3 ties at a step of 10 centimeter in each confined region, okay, until the end of the critical region, which is the end of the first floor. And now, as you can see here, all the prescriptions are satisfied. Okay, so as I mentioned, there are several ways to export the reinforcing that you have defined in the VIS model in order to start the true detailing phase. The first option is to export the tabular layout of the different column rows and beam rows. And this can be done selecting one or more elements, so one or more beam or column row, and click on Export Rebar Table. You can export the rebar table and then look at the rebar table that includes basically the name of the member, the segment of the member, the length of each segment, and longitudinal and transverse reinforcing assigned. The second way is to export the reinforcing layout in DXF format. You simply have to select one or more element at a time and click on Export. This can be done both for beams and, for example, columns, and also, for example, shear wall. Let me select the same shear wall. Okay. And what you will obtain are some DXF file that can be used as basis for your detailed drawing. Okay, these are in the correct. All these drawings are in the correct scale. Okay, this is the first beam row that we have. Okay, users need to basically manually account for splicing and overlapping of rebar, but for example, we can simply move this in the correct position. Okay, so this is a very good starting point for the detailing of the beam row. The same, you also have the detail of the different section with the name and the segment to which this section is assigned. So here the segment subdivision is reported, and for each segment you have the corresponding sections assigned. The same can be done for column rows. So all the columns that belongs to the same column rows will be placed in the same DXF file, and again you can easily overlap the element and the side where, well, in this case splices are already made because the program, as you can see here, correctly report the splicing. So since columns are spliced at each story, the job in this case is even easier. And in the case of shear wall, we will have a set of sections and the related reinforcing information for each of the sections of the shear wall. Let me open the file. Okay, so this is the base section, the elevation. We identify the confined region. We tell which is the length of the confined region, the thickness, the height of the section, and all the information related to the vertical and horizontal reinforcing assigned to each of the section that made up the shear wall. As I mentioned, the last option, which is currently still not available, but it will be available in one of the next version of the program, is the possibility to export the structure reinforcing included in IFC format. Okay, so we can export the structure, and in that case we can open it with every IFC viewer. For example, we will now use Solibri. So, and take a look at the reinforcing that we have defined into the different elements. This is particularly useful to have a better idea of the level of the congestion of the reinforcing in different elements, especially in the intersection regions between different elements. Okay, this is the structure. Let me select the reinforcing. make unselected invisible. Okay, and so we can take a look to the reinforcing that have been exported in full IFC format. This is done for beams, columns, and shear wall as well. So also the transverse ties that we placed have been put there, and so this will be this is one of the latest features that we have added and will be soon be available to all the users. Okay, so basically I have concluded what I wanted to show you in this webinar. Let me know if there are any questions. As last thing, I would like to encourage you to answer to the survey you will receive at the end of the webinar, because as I mentioned, your feedback is very important to us, and we will use it to keep improving the program and hopefully to making it even better. Okay, so I don't see any questions so far, so I assume that it's all for now. As I mentioned, okay, now I see some of you raised the hand, but I cannot open your audio. Joao Catalao, please, if you can please write your question in the chat, I will be glad to answer you. Okay. So I'm waiting for questions. If you have any kind of question, please feel free to ask. Thank you, Nick. Okay, still don't see any question yet. Okay, so I assume that we are done. So thank you again for joining this webinar. See you on the next one. In the survey, you can also suggest us which could be the topic of. Okay, Joao Catala would like to know if there is any drawing customization possibility. Well, the only possible customization is to choose whether the splicing in the column should be done at the base or at the mid height, while for the other aspects, the drawings reflect basically what you have put into the elements. So the drawing representation is standard. It cannot be customized. But if this is something that is important, or if you have any idea to share with us, some simple suggestion to make it more flexible, more productive, you're welcome. So again, thank you to everybody, and see you on the next webinar. Goodbye.